Hi everyone, I am Sanya Kuller, and in this video I'll be talking about how you go from a conditional probability distribution table, a CPD, to a Bayesian probability tree. So yeah, this is a worked example that we'll be going through, and at the end of this, I really hope that if you're given a problem that's similar to this problem, for instance, so please give the most compact tree. That is the one with the fewest nodes that can represent the probability distribution, the probability of D given A, B, and C that is specified by the conditional probability distribution table below, the CPD table below here. So if you're given a table like this, how do you represent this as a tree? That is the main question that we're going to talk about today. How do you represent this thing as a tree here? You can see this like little tree, and it's, how do you represent not just a tree like that, but I mean like an actual tree. So what we're going to end up seeing through this is that, if you're given, so basically what we're going to end up seeing through this is that if you have this conditional probability distribution table for D, so these are the probability distribution of D given a D being true or false because it's a Boolean random variable, given these values of A, B, and C, how do we take this table and then transform it into a tree like this? So this is the outcome, and if it's intuitive to you from looking at this image, how to do this, looking at this right now, this is the answer. So we're sort of starting with the answer. So if it makes sense to you from this, then that's great. So this is great for visual learning. If you can just see this together, then that's great. But otherwise, I'm going to walk you through step by step. How do you do this? How do you take this table here? How do you take this table here and sort of represent it as a tree? How do we even arrive at this? Because sometimes I know that myself, like sometimes the math professors or math teachers used to put up a solution, and then I'd be like, oh yeah, that makes sense. But then if I was given the same thing again, I would struggle, and I would say, okay, how did you do that? Like, what is a thought process that goes beyond this? So that's what I want to walk you through, because when you see it like this, you're like, yeah, that makes sense. But then how do you reverse engineer? And I have a younger brother, and I have a lot of experience in helping him out with some of these questions too. So how do you reverse engineer this situation and figure out what exactly and how exactly I arrived at this? Because ideally, yes, you want to be able to understand how you go between this and this. Like you want to understand that, yep, that this is representing this table, this tree represents this table, and vice versa. And I have another video talking about how you go from a tree to the table. And so this would be another great practice for that. But ultimately, you also want to see, how do you go from the table to a tree when you're given a different situation? How do you figure this out? So please watch the rest of my video if this part like doesn't make sense to you, because I'm going to be going over that part slowly. But in any case, this is a work solution to a conditional probability distribution table here for D, all the way to a tree representation of the same. So in this situation, we observe four random variables that are Boolean. They're true and false. Like boo, liar, what you say is false. So A, B, and C, they impact D here. So the way to see it is that we have A, B, and C, and they all have some role on the probability distribution of D. You know, the probability D is true or false, for instance. So all these three random variables that are true or false, they all impact the probability distribution that D is true, and therefore the probability that D is also false, because the probability that D equals true plus the probability D equals false equal 1. So what you're going to see here So what you're going to see here is that in this conditional probability table, the CPD, conditional probability distribution table, for the probability of D being true or false, it's based on the values of A, B, and C. And this part of this table sort of tells you the breakdown of what's the probability that D is true and that D is false given these three random variables A, B, and C here. So that's what we observe here. We have these three random variables and a Boolean, so there are true or false. And here are 8 possible values because A can be true or false, and B can be true or false, and C can be true or false. So we have like 2 times 2 outcomes for each of them times 2, so this is 8. So for each of these 8, so this is the first one here, second, third, fourth, fifth, sixth, seventh, and 8th. So these are the 8 values here, and then we have the probability that D is true or false given these 8 possible outcomes. Like the first one is all 3 of them are true. A is true, B is true, C is true. And given that D is 50-50 chance of being true or false. Then in the second case, A is true, B is true, but C is false. And given this information, probability that D is true, given that A is true, B is true, and C is false is 25%. But the probability that D is false instead, given that A is true, B is true, and C is false, is 75%. So these probabilities really differ. So this is what this tells us. This is the conditional probability distribution table for D given these values here of D, and these all sum up to 1, sum up to 1, sum up to 1. Each row sums up to 1 because D can either be true or false. But its probability is so based on this. And one thing we want to do is represent it as a tree that is compact. So no nodes that are extra. It's sort of giving the gist of this table and the easiest way for us to understand. Almost like a decision tree. So we're going to be like painters mathematically constructing a tree based on a conditional probability table, distribution table. So PD given ABC is the probability of D given the, so it's the probability of D, probability of D given the random variable. So that's what this bar represents, given the random values for A, B, and C random Boolean variables. So these can be true or false. So what is the probability of D? So just again, since it's a probability, so probability of D, being true or false because it's a Boolean. So what is the probability that, so we look at this distribution for D and we have, probability that D equals true. And then we also have the probability D equals false. And that's what we are concerned with. And these both sum up to 1. But we are looking at, whatever these numbers are. And number 2, number 1 plus number 2 have to add up to 1. But, we're trying to find the probability that, of D being true or false, given the random variable values that we observe for A, B, and C. So that's what this probability is. So it's a conditional probability that is dependent on what we observe for A, B, and C. And that's what determines the probability distribution for D. So what you can better see now is that there are these 3 groups as well that I was talking about, the 0.25 group and 0.75. Then there's this group here of 0.5 and 0.5. And then there's this last group of 0.75 and 0.25 here. You can better see that there are these 3 groups here. There's a 0.25 and 0.75 group here. There's a 0.5 and 0.5 group. And then the 0.75 and 0.25 group here. So we're trying to group the probability distribution values of D into these 3 groups. So basically, these are the 3 groups. So we found 3 different groups of probability distributions for D. This is an orange group here where we see that D has a 25% chance of being true, 75% chance of being false, and then here, where D can be 50% true or 50% false. So these are the 3 outcomes in this group. There's 1 outcome in this orange group, and then there's 4 outcomes in this group for D, where 75% of the time D is true and 25% of the time D is false. So basically here we have three different groups of probability distributions for D here: orange, yellow, red, and we want to group the random variable values as well. So not just like these values for D, these probability distribution values, but also the random variable values, like what are the groupings that we can identify here. So in the process, what we're going to do is we're going to see, okay, these true, false, these are all the 8 possible different outcomes for A, B, and C that we have here. And we're just going to see, like if we look here, this is false and false for A. So I group this as false, a giant false, and this part here becomes this part here. And this is true and false for C. So these are the same rows, but the only difference is that C is true or false. So that's what this is here, true or false. And similarly, this whole part here is all false, so I've made this all false. This part that's all true, I've made that all true here. These two that were false, I've made that into a false. So basically here, what I noticed is that these are true or false, and that's what this is, true or false, and then these were true or false. So it ends up being that we're going to ultimately say that whenever B is false, it doesn't matter here what A or C are. We're always going to observe this 0.75 probability that D will be true, and this 0.25, so this is 25% probability that D is false. So it doesn't matter what A or C are basically. As long as B is false, then that's all that kind of determines the probability distribution for D. So that's sort of like some intuition that we can gather from here. So again, we just see that for all 4 values when B is false, this is what we observe. So this is sort of like the way we summarize it into different groupings, the 3 major groupings, and then trying to get some intuition, some analysis. And I remember, Yang-Shi, when I was learning these concepts, they sometimes used to be so hard. Like, how did professors come up with these ideas or insights? Like, how did they sometimes just know what it is? Like, how do they know where to go? So that's what I hope that this can help you learn. So then what we're going to do is we're going to try to construct trees for each of these 3 probability distributions. And see, like, so there's this orange one here, the yellow one, red one. But I'm trying to show you that for the orange one, A is true, B is true, and C is false. And this is one of the ways we can go about it. We can say, hey, A is true, then B is true, which is what we have here, and then C is false. So this orange corresponds to this part here. So we can say, okay, A is true, and B is true, and C is false, and then probability D is true is 25% here. Probability D is false is 75%. And then you sum them up, and then you get 100% actually. So that's what we could observe from here. And there are other ways. So if we're just focusing on this orange thing, we can say, okay, we look at A being true, B being true, C being false, like what I was showing. We could also, who's to say that we can't start with B being true, A being true, next, C being false and getting the same distribution, or we can look at A being true, C being false, and then B being true. And then the 3 other configurations, it's just the ways to order them. Like we could also have like B, C, A. We have ACB, we could have CBA, CAB like cab. There's so 6 total configurations for this tree alone. So sometimes you might be wondering, like, how do we even know where to start? Like that's a key question, I feel. So what we're going to think about, he's going to have some initial intuition. So we're going to see that it appears as though the value of B, if we're looking at this table, what we're saying is that, like what I sort of told you, what I saw here is that if B is false, doesn't really matter what A or C are. And in fact, we can just kind of just write this as like, T or F. It doesn't matter. It doesn't even matter what A or C are. It's just going to be 75% chance that D is true and 25% chance that D is false. So that's what it's going to be. So if B is false, it doesn't matter actually what A or C are. So B is a key role. Like, so it appears as though the value of B has a main impact on what we observe for the probability distribution of D. So that's actually like a huge thing. True or false, it doesn't matter. And then what we see is that there are many outcomes here, but most of the time, if B is true, then 50-50 chance. But there's also a situation where when B is true, then, it could be 25% chance that D is true and 75% chance. But I'm going to break it down for you and sort of show that, we look at all these 8 total outcomes and we see the impact of the value of random variable B on the probability distribution of D. So as a Boolean, B can be true, which is T, or false, F. And, it is true for 4 outcomes here. B is true for 4 outcomes, and it's false for other 4 outcomes, because there are 8 outcomes, and so 4 for true, and that's the same for A for C. So basically, then what we observe is that we look at B and it can be true or false. So out of the 4 times what we have observed from here is that whenever B is false, the probability D is true is 75%, and the probability D is false, this part is 25% here. That's what we've always observed. So it seems to be pretty telling. So we want to make the simplest tree where we identify the variable that has the biggest influence in impacting that. And that's what we see when we observe this, that hey, like, when B is false, then all the time we're noticing that, this is the probability distribution for D being true and D being false. This is the probability distribution for D. And that's really huge, right? Like one value, it doesn't matter what A or C are, this is what you're always going to have for D. 4 out of 4 times, 100% of the time we're going to observe this. And again, this is just an example, so it's very dependent on what example you have. But then if B is true, so the other 4 times that we're noticing is 1 out of those 4 times, 25%. So 25%, we're going to notice that 1 out of the 4 times, so these are the 4 times here, this first half when B is true. So 1 out of those times is it the situation when D being true is 25% and D being false is 75%. But in general, 3 out of the 4 times we observed the probability D is true is 50% and the probability D is false is 50%. So based on this finding that B can explain like a lot of what we're observing in the probability distribution of B based on the specific example, we may consider B as our first variable here and the first node for our tree. It's going to be the root node. So the root is like the parent, the grandparent, whatever it is. It's the first node. So we're going to say that B is a key point in this tree. It's almost like a decision tree, so to speak, where like if we immediately know that B is false, that this is the distribution for our variable. It's explaining most of the variation in D as well. So if we know B is false, automatically we're able to assert this. So we want to be able to have the simplest tree where we don't have to worry about what A is or C is. We just want the simplest, most concise way for us to understand what is driving the distribution of D. And this variable, unlike A or C, gives us the power that, boom, 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 this is all false. And it doesn't matter what A or C is, it's this, you're going to have this distribution for D. And most of the times, if B is true, you're going to observe this for D, but maybe 25% of the chance you're going to observe this. But it does have a pretty consistent role. And that's why we're going to use it as the first variable, because instantly, if B is false, we just want to come to the conclusion that D is going to be true 75% of the time and false 25% of the time. We want that conclusion. So that's why we're going to try B right away. If we started with A or with C, we would have to like then ask about B or vice versa. Like if we looked at A being true, for instance, A being true is here and also here and also here. So it doesn't make sense to split on it right away. If we look at like, and C similarly, C being false is here, C being false is here, C being false is here, true is here, true is here. And maybe this is one good thing, that if C is true, we know that like it can't be this, but it's just kind of haphazard. But you might see a clear pattern like this if you try to look and try to gather this intuition. So I'm trying to teach you how we gather the intuition. So that way we go back to this initial configuration and we see that B is one of the most important variables and is our root variable. So remember I said that there were 6 configurations for this first part where, true, true, false. We're going to then just focus and hone in on situations when we start with B. So we can look at B, A, C, or B, C, A, B being true, A being true, C being false, or B being true, C being false, A being true, and try to sort out the tree this way. And basically, when you see something like this, whenever we have a random variable that is true or false for the probability distribution, then it doesn't really matter for the outcome. So over here, what I want you to see is that it doesn't matter here what these are. Essentially, if it's true or false, all we are gathering is that so I just sort of consolidated these together into true or false just to make it simpler. But what happens is that if C can be true or false here, it means that C doesn't matter for the situation. If A is false, and so you can just see this as a continuation of the same. So if A is false, B is true, then C can be true or false. And if here A can be anything, C can be anything, it doesn't matter if B is false, and that's what we observe. So that's kind of like the main idea. So when it's just true or false, we just want to put a smiley there because we're like, hey, it doesn't matter. We don't even need to know what this is here. So we don't need to know as long as B is false. That's all that matters here. And that's sort of like what we care about is like we look here and we see, oh, it doesn't matter if A is false and B is true, which, for all these outcomes here. So this is like A is true, B is true, C is true, and this is a distribution, or A is false, B is true, and C can be anything, and this is what we get. So that's what the smiley is telling it. Hey, it can be anything. It doesn't make a difference here, and that's what we get from summarizing the eight outcomes that I was showing you earlier. So please do write this down, and please do reach out if you have any questions on this, though. So yeah, this is sort of like what we then see. So I'm just going to jump to this example, for instance, because this one's a little bit easier. So what this is saying is that A can be anything, C can be anything, doesn't matter. As soon as B is false, this is the distribution that we observe. And the probability D is true is 75%, and the probability, basically, the probability that D is false is 25%. That's all that matters. It does not matter what A is. It does not matter what C is. If B is false, then this is what we observe here. The probability D is true is 75%, and the probability D is false is 25%. And that's what we got for that one. So that one was very simple. So in this situation, we can do it many different ways, but I think C can be anything. So it seems like C does not, so we can see that C, pun intended, wordplay, C does not have any role here. But if what we are seeing is, okay, the first one we decided on is that we're going to start with B. And that's what the previous example showed us, that B being false, instantly we get the distribution for D right away. So we're going to start again with B. So B is true. And then we see that, hey, C doesn't seem to matter as much. But what we do see is that A is important and is true and false. So we're just going to then start with A here and then say that, okay, B is true. And A can be true or false. And then if A is true and C is true, then we observe this distribution here. So I didn't want to keep writing it over and over again, but we have these three nodes, this one, this one, this one. And so if B is true, A is true, C is true, that's what this thing is showing you here. That's what essentially this part here is sort of showing you. It's sort of showing you this part right here. That's what it's showing you, that L-shaped part. And then the other situation is that B is true, of course, and then A is instead false, which is what we have, and C can be true or false. That's what the smiley says. It can be anything. So I just listed it out like true or false here. So this other part right here, this part right here is sort of like what this part is representing. So, false, true, anything. B being true, A being false, C being anything. And since this shows that it can be true or false, but we don't even need to include that per se. That just means that C is just not important. So let's just go and slash out C because C doesn't matter. So we can see that C doesn't matter here in the situation if A is false. So we just get rid of C. And that's why it's not important, and we're just going to eliminate it, and then we just have this as what our tree looks like. So basically, if B is true, and A is true, and C is true, then we have this distribution. Or we can also get this distribution if B is true, A is false. No questions asked. If A is false, then C can be anything. It doesn't matter. We get this distribution for D. So that's like sort of like the major intuition. So we had this from before. So again, we grouped the probability distribution of D, like for those 8 outcomes, we had grouped them and found that there were those 3 outcomes where D can be true 75% of the time, or 50% of the time, or 25% of the time. So we had those ideas, like that we got like those 3 groupings, and for each of the groupings we also then saw overall that it seems that B plays a key role, especially because of this situation where if we know that B is false, then instantly we have this. So we want to ultimately combine these to form one tree. So why not just look at the situations where B is the root node? That's what's really important, is looking at where B is going to start. So that's where we get B here. Then we also looked at this where B is starting. Then we could look at C and then A. But if you think about it, you're going to land to the same conclusion, that C doesn't end up being important. Because, if A is false, then you also get to the same conclusion here. So you don't even need to use C. So it's sort of like you're going down the priority list, like which one is the next important. And what you might learn in decision trees, and I'll try to put some videos on this too, is that sometimes you look at Gini or entropy or other things when deciding where to put splits, which variables to split on when you're coming up with a decision tree. So the same idea comes that you want the most important variable to be at the top, and a second most, and the third most. And once you have this, it gets easier, because you're like, hey, B is super important. So if I'm going to combine all these trees together, I must have the same root node for all of these. So I'm going to want to put this tree together and this tree together, and then select one of these two, and ultimately combine the 3 into one. But what I observed from this one is B is important, then A is important, and then C. So this already kind of gives me the idea that I should get rid of this one, because the second most important from this tree seems to be A. So I want to do something like a B, A, and a C. So I want to go with something like this. So the root is B, it's the top node, it's the parent. Then A comes in priority, and then C comes. So I want to do something that's like a B, A, and C. And again, guys, there's so many ways to do this, and I really hope that this is not going to confuse you guys, the fact that I'm like listing out all these steps. Like if you see from the beginning when I showed you the 8 outcomes and the final tree, if that makes sense to you and you can reason that out, then great. But this is sort of like a tool for those of you who are like me, who might just need to figure out like, how do we make sense of this? And maybe along the way, some of what I was saying didn't really gel with you or resonate, but you found some other way through it. And if that's the case, then I'm happy, and please comment on what worked for you, and please let me know how I can be better in that way. But this is like what's really key, that you start with B, and then the next important is A, and then the last important is C here. So the order is B, A, C. So we got rid of this outcome. So we're just like honing in on it. And maybe you could already see this if you're thinking, how do I like overlap? Like how do I like kind of combine these different things together? Like how do I make sense of those things? Like how do I plug it in, overlap, overlay these trees together meaningfully? That's sort of what you would try to do naturally, but I'm trying to make it down to a science, because something that really like mattered to me and I would be kind of lost on is like, how do we have intuition? Like how do we know certain things? Like people often say that in math class a lot of professors would sometimes show the proof and how they got there, and I'd be left wondering, okay, it makes sense when they do it, but if I did it myself, like I don't know if I would be able to understand that. And I was so blessed and fortunate to have professors who would meet with me sometimes for an hour to go through how to go through certain proofs, how to think through problems, how to approach them, because each problem is unique. But like sometimes I'm trying to see how I can improve those reasoning skills that you guys have, and how I can sort of take what's tricky and put it down into a science, so that if any of these click along the way, then that's what would make me really happy if this works for you. So ultimately, I've shown you how I selected the 3 variables in the order of priority, B, A, and C. And this was the main reason, again, for why we chose B. as first, and this is the reason why we chose A as being second important, because it's if you know that B is true and A is false, you instantly don't even need to know C, and you can come here. And then based on this idea, we can select two of the variations that began with B, and we selected B, A, and C because of this order. So if you then see, how do I overlay these? Well, you start with B being false. Probability D is true is 75%. So this part is taken care of. Sweet. That part is taken care of. Awesome. And then the next thing you're going to see is B is true. Okay. And A is false. That's what this part is. 50% probability D is true. So we just put the probability D is true here, and then you can always know that the probability D is false. It's just 1 minus the probability D is true. So that's what this is. And so now this part over here is basically already taking into a consideration this part right here, under here. That part was taken care of over here. Great. And then this part where A is true, and over here now, if A is true and C is true, we have the probability D is true is 50%. So this part is here. That's great. And then lastly, we're going to see, okay, what if C is false? So that's how we sort of overlay this variable. C is false, but A is true. And then you'll naturally see this thing come into play. Like if you just say, how do I combine them together? You're going to want to have, essentially when you have a tree, you need to have all outcomes considered. If you have B here, you need to have its false outcomes and its true outcomes, because you need to have one outcome be true. So B can either be false or true. You need to consider and exhaust all the options. So B can be false or true. So we had to consider that A can be false or true. We consider that, and C has to be false or true. But we don't need to then consider, okay, B or C. Like that's sort of like a tree that you can get the same information, but it's not helpful and it's redundant and it's going to be stressful, because we don't need to know like if A is C or C is true, as long as we know B is false. And we have this, for instance. Like, why go through that? We only need to worry about A and C, especially if B is true. Then the next question we're going to ask is, if A is false, then we know that D has a 50% chance of being true. But if that's not the case, if A is true, if it insists on being stubborn, if A is true, then we have to see if C is true here or if C is false. And we come down to this situation right here where we're seeing if C is true or C is false. That's the last decision we have to do, and that's going to determine if it's false, then 25% chance that D is true. But if C is true, on the other hand, then 50% chance that D will be true. So that's sort of like how you can combine them together. And you need to make sure, again, that for each variable, you can't like have something like this. You can't have it like with that. You need to have both outcomes on the tree. This little tree will be happy if you exhaust all the outcomes. You need to really have all the outcomes there. And again, this part right here that was highlighted in yellow is this part, last part there. So you really need to exhaust the outcomes. So all in all, I really hope that I was able to show, like, so if this part to this part did not make sense, I hope that my methodology is able to help you explain how we can give the most compact tree. No extra nodes, no nothing. We don't even have to go down this path of like A or C or other things. We don't need to do that at all. We don't need any of that. I hope that I was able to show you. So if this part is not intuitive, and it's probably not for a lot of people, maybe with a lot of practice you could get here. But what you need to do is to break it down if it doesn't make sense. And that's what I hope my video is able to show you guys. So please let me know if this helped you, and please like and subscribe to my channel if this was helpful, and let me know if you have any questions at all either. But the key idea that this is how you go from a conditional probability distribution table to a tree that is concise, that gives you the idea basically that if B is false, whenever B is false, it doesn't matter if B is false. Like, and you get this idea by rearranging the rows, finding the probability distributions as well. And you find that this is sort of how to go about it, that as long as B is false, you always seem to get this same idea. And a key thing in data analysis as well is sometimes rearranging the data, making sense, making patterns, finding patterns, signals from noise. And that's what my first idea is, just to group the data, organize it, and just try to systematically pair the data and find what those stories are. And if you do need many iterations of trees to find that, then that's also fine. I do recommend coming up with the whole hairball tree maybe, and then saying, oh, I don't need this, so I need that. But then again, that might be complex and you might get overwhelmed, but that's still a strategy. You can just draw out variations of the trees till you find something and you're like, I don't even need this. Like how I showed you how I slashed out a part where we had C, true, and false. It's redundant. You might come to that conclusion. You might have like a tree that's like taking up the whole space, like a spider web almost. And so be it. But I just hope that this was helpful to you guys. And yeah, please let me know again if you have any questions. And I'm going to end with my little logo of a star, which is also there as well. But like, I just hope that this is helpful. Ah, thank you guys.